レイトレーシング、次世代のフラグシップスマートフォンで究極のゲーミング体験を実現と題しまして、ARM 応援ウー様よりご講演をいただきます。それではよろしくお願いいたします。
はい、皆さんこんにちは。私はオーウェンです。今日は日本語でプレゼンしたいけど、日本語がまだ苦手だ。それで英語でプレゼンしていきます。通訳さんに翻訳してもらいます。では始めましょう。So now I will switch to English. Sorry about that. So today I will talk about the ray tracing technology on the mobile device. Okay. So you can see from the slide, Immortalis is on the new flagship GPU. Is designed to provide ultimate gaming experience on the next generation smartphone. And it's also the first on GPU to offer hardware-based ray tracing on mobile, pushing the mobile gaming on Android to a whole new level. So about today's agenda in this presentation, I will first talk about what ray tracing is and what it can help you to achieve. And then I will take you through some of the techniques we explored and with some technical details for each of these. And finally, some advice for you to write efficient ray tracing application. And finally, I will introduce the tools and the resources later are available to help from ARM. Okay, so let's start with a brief introduction to ray tracing. So the first one is we talk about the typical computer graphics scenario. We would have it's a rasterization pipeline. We will have a camera, a light source, and a 3D fractal contain the scene we wish to render. With the traditional rasterization approach, we submit the work to the GPU object by object. We transfer and project the geometry as triangle primitives onto the screen. Then we will then check for which pixels are covered by each triangles, and then we determine the color of those pixels based on the model's material properties. So then we repeat this process for each object in the screen and resolve the situation where one object is behind another by checking their depth value stored in the depth buffer or Z buffer. So that's a traditional way to render a scene. And the ray trace, okay, you can see that it's a rabbit, and we render rabbit first, then we render the tree, something like that. Okay, then in contrast, ray tracing is a completely different approach that simulates how light travel in the real world. So we model a light as a rays that leave a light source and travel in all directions, bouncing off a surface until eventually they reach our eyes. Or in this case, our eyes, or in this case, a camera sensor, forming an image. But many of these rays will not reach the camera. So to be more efficient, we usually do it in the other way around and trace the ray from the camera into the scene, one ray per pixel, so that we can then check what is the closest object that reach ray hit. What is the closest object that each ray hit? And this way paint the final image. So note that I think I have. Note that we do not need to stop at one ray per pixel. We can keep tracing ray in multiple directions to gather more information about the surrounding surface and construct more photorealistic image. Again, many rays will miss the light source and make the pixel appear darker, giving us a noisy image. Although we can improve it by tracing more and more rays, but it could be more and more expensive for real time. So today I will only focus on the hybrid approach that combine the speed of rasterization with the power of ray tracing to improve the visual quality of the frame. And here is the animation. You can see the light hit the object, then finally reach the camera. But we do the inverse. We hit a ray from the camera and see what we hit. Okay. So if you are not familiar with the ray tracing technology, there are 3 free books you can check online. They are free. Those books cover the most common ray tracing technology from basic to advanced, and you can check it online. Here is the QR code you can scan. Okay, so here are some effects we are currently exploring. We can use ray tracing in mobile graphics and other effects like shadow, reflection, and the refraction and the global illumination. Note that we go down this list. We needed to trace more and more rays, and therefore the effects becomes more and more expensive. So we can sometimes get a good quality result with fewer rays by using ray denoiser, but today I will only focus on the effects which can achieve noise-free result with just 1 or 2 rays per pixel. So I will talk about the hard shadow, mirror reflection, and the smooth refraction. To demonstrate this, I have prepared a video showing a scene we used internally to experiment. So we can see the video. Okay. So in this indoor scene, we are using ray tracing for reflection on floor and walls, and the refraction through the glass cube in the middle of this one. And the pixel perfect shadow all around the room. So you can note how reflection and the shadows adapt to the fast moving object. And the ray tracing can achieve accurate and high quality results at a high frame rate. So this demo is running on a mobile device, the latest Immortalis GPU. Okay. So here are a few more technical details about the demo. So it is based on the Cronus Vulkan sample framework, which is open source and cross-platform. So we could develop the application on desktop and easily build for Android anytime. And we are actually using defer shading After saving color, normal steps, and other attributes on the scene into a gbuffer, we compute the lighting of each pixel, and then use ray tracing to render shadow, reflection, and the refraction as a post-processing. We use it as a post-processing effects, then combine them all into the final image. This way, this was useful to analyze each effect in isolation and to explore some optimizations such as computing the effects at a lower resolution. With this pipeline, we can achieve around 40 frames per second on mobile device with on Immortalis GPU, and we believe there is still room for optimizations. So as I mentioned, we are using the Vulkan API. This demo is using Vulkan API, so now I will briefly introduce the Vulkan ray tracing extensions. So for ray tracing, the first thing we need to do is we need to have a acceleration structure for our thing. Acceleration structure is actually a structure which organizes the geometry so that we can efficiently narrow down the ray. Narrow down the ray intersect. We need to use the VK-KHR acceleration structure extension, and although the actual structure is opaque, so it's and it's defined by the vendor, GPU vendor, but it's usually a kind of a tree, and the API gives us some option to control the topology and keep it balanced. So the API then make a distinguish between bottom level and the top level acceleration structure. Bottom level structure contain the actual geometry data, usually triangles, but it could be some mathematical defined models like a sphere or box. This data is then usually organized in a hierarchy of bounding variance. So that we cast an array, we can minimize the number of triangles intersection check. In the case of the model on the right, we could only need to check through the triangles contained in the green box, and that are intersected by the ray, and just ignore the rest. So it will be much faster. And the top level acceleration structure then use instance to group the bottom level structures with other properties, some, such as transform metrics, which can be efficiently updated for some animations, and a custom ID, which we can use to define a material. For example, note that we can efficiently have 2 copies of same model, use the same bottom level structure as a video, as we do in the video, the flying drones in our demo. So now we have a section structure to define our scene. Then we need a way to define and trace array. And for Vulkan, they offer 2 options. So the first option is use a VK-KHR ray tracing pipeline. As with Vulkan compute and the graphic pipelines, we need to define a set of shaders. Actually, 5 types of shaders we need to define. Later, we'll control the GPU operations. In this case, to generate and trace the rays on our scene. So in the original orange, in the orange box is the shader we shall implement. So first is a ray generation shader, which defines the origin and the direction of each rays that we wish to trace. As the GPU traverses the acceleration structure, it may call an intersection shader if it intersects user-defined geometry, or any hit shader if it intersects transparent geometry, for example. So otherwise, one of two things can happen. Either the ray does not hit anything in the scene, in which case we can call a miss shader. And the sample environment map, for instance, or we hit opaque geometry, and in that case, the GPU invoke our closest hit shader. In this shader, we can then determine what data we will need from the intersected object and return that to the ray generation shader. For instance, we may sample the color from the object's material. So this approach gives us a lot of control, which can be necessary for certain techniques, but for the effects we will discuss today, however, this extra complexity is not necessary, and instead we will focus on the second option offered by Vulkan, called ray query. So the ray query, if we want to use ray query, we need a VK-KHR ray query extension. So it gives us the option to bind a acceleration structure to any of our existing shader, such as our fragment shader or computer shader. We can use ray query inside these shaders. And this means we need to manage the ray traversal ourselves. So, but as we will see, this will be very simple to do for our purpose. In the shader, we will first define a ray and then start a traversal with a function call. After this function call returns, we can then use the API to check if the traversal is complete, or if we need to process more cases, like transparent geometry, and then continue the traversal. So once the traversal is complete, we would either have hit something or missed. If we hit something, we can query some data, such as distance to the object that we hit, and use the result in our shader. I will soon show some code to demonstrate how this works. And for hybrid rendering, this approach is usually more suitable and efficient than the ray tracing pipeline. Now we have understand the acceleration structure and the ray query. Now we can describe how to implement our effects like shadow and the reflections. So let's talk about shadow first. So we can achieve high quality shadow by tracing one ray per pixel toward the light. So in this case, for the pixel on the plane, you can see on the left side, the rabbit and the plane. For a pixel on the plane, we can see that some pixel will hit the rabbit object as they travel toward the light. And those are the pixels that will be in shadow. With a traditional shadow mapping technique, we would usually need to render the scene multiple times, right? Which can be very expensive, and often must deal with some artifact due to the limitation of the resolution of the shadow map themselves. So all these artifacts can be simply avoided with ray tracing. As a simple optimization, we recommend to first check the angle that the ray makes with the surface normal. If the angle is less than 90 degrees, we can proceed to trace a ray. But if the angle is greater than 90 degrees, we can then determine the pixel is in the shadow, right? Without tracing a ray, because we can assume the line is behind it, like the picture shows. So now we can see the video. We can see the shadow in action. You can see that we have two shadow casting lights, which require at most two rays per pixel. Here is a debug view showing the shadow in isolation. As we move close to the shadow, note we can achieve a high quality level of detail without any artifact like a shadow map will do. And of course, they are updated in real time with animation. Notice how they scale and deform accurately over the surface in the scene. So that's a debug view. So we isolate the shadow path. Okay. So here is how the jQuery API looks in our shader. This is in fragment shader. So just a couple of simple function codes. In this case, we define our jQuery context and initialize it with our race origin and the direction. Then we start a traversal of the assertion structure by calling the jQuery proceed. Okay. To check the intersection, we call a jQuery get intersection type function. If we have not missed, that means we hit something. Something will stop the ray from reaching the light source, and therefore the pixel should be in shadow. So since in this case of shadow, we do not care what we hit. We only care if we hit something, and we do not need to. We do not need the closest hit. So we can accelerate the traversal by using the special flags. As you can see from the code, we use the flag terminate on first hit. So when we have a first hit, then we stop the traversal. And the opaque flags. So we only want to check if we hit opaque object. We don't need to check the transparent object to ignore the transparent geometry. So if we use those flags, then we can get it run faster. Okay, then I will talk about how to implement the refraction and the refraction. So for refraction and the refraction is more complicated because we don't only need to determine if our ray hit something. We also need to know exactly what we hit. And since we use use that information to retrieve the intersect object's color. For that, we need to be able to access all data. For all the objects and the materials in the scene. So in this case, we can use a Vulkan's descriptor indexing to define an array of buffer and the textures that we can access using lookup table. So to index this table, we can use the Ray Query API obtain instant ID, like the picture shows. We can obtain the instant ID and a geometry ID and a primitive ID from the assertion structure. And we may see here how in our scenes we have 4 instances, one per moving drone and one for everything else. And within each button level structure, each geometry also has a unique ID to represent here with a random color. You can see the picture on left side. Each color means instance in the assertion structure. As we build the assertion structure, we keep track of how many geometries each instance contains, and make sure that everything can be identified uniquely using the sum of the instance ID and the geometry ID. Then we build a set of lookup table so that with the unique identifier we can access everything that we need to render the final image. Okay, so with the primitive ID, we can access a relevant index buffer and retrieve all the vertex attributes, including textual coordinates. And the API also provide barycentric coordinates of the intersection point so that we can use it to interpolate the attribute. And we retrieve the material ID in different table and use it to index into our texture array. Finally, we use the UV coordinate to sample the texture and compute the final color. So for reflection, all we need to do is to calculate the reflection direction, trace array, and blend the color of the object and the reflected object. Calculating the direction, reflection direction is very easy because GLSL provide a built-in function called reflect. So we can use it to calculate the reflection direction by giving the surface normal and the vector between the camera and the mirror pixel position. So ray traced reflection can handle a situation that traditional approach, such as screen space reflection, cannot, like a reflection of the objects located outside of the screen, outside of the camera view. So in our demo, we are exaggerating a reflection for demonstration purpose. But most of the time, since they will be blended with the color of the reflective surface, we could optimize the technique by simplify the calculation of the reflected color rather than using a full PBR. So here you can see how this screen looks with reflection, turn on and off. You can notice how reflection can deal with the corner case that would be impossible to handle with screen space reflection. Like the bottom part of the drone or the whole drone when it's off screen. With traditional rasterization, we would probably need to submit a new draw code for those objects which are outside the screen to achieve this kind of effect. So here we are using only one ray per pixel, but we don't need to stop there. We could also trace another reflection ray at the intersection point in order to achieve a reflection within reflections. Like in this case, reflection on the wall are now visible in the floor. So again, this would be very hard to achieve by using a traditional screen space reflection. So you should be able to see the reflection in reflection. That means recursive reflect. Okay, then let's just talk about the refraction. And the refraction is actually simulate light traveling more slowly as it transmits through different media. In our case, we have air and glass. As the light travel more slowly through the statue, it changes the direction and cause it to show a distorted view of objects on the other side. So to calculate the change in the direction of the rays as they travel through the glass, we can again use GLSL's built-in function called refract, which takes incoming direction, the surface normal, and the ratio of indices of refraction. So here we show the refraction on and off on the statue. Notice the distort on it as we move around. We can check the video. Yeah, you should see the reflection in the characters. Okay, once again, this would be very difficult to achieve with rasterization techniques. We could approximate it by rendering back face and using the back normal to sample the environment map. But this is very limited and cannot easily handle the animation objects. We could also fake it by render the scene behind the statue to a texture and filtering it to make it appear distorted and blend it, the result. But with ray tracing, we are actually replicate how the light would behavior in reality, so achieve a more realistic result. So reflection and the refraction are very tricky to handle in traditional rasterization way, and ray tracing can simply resolve the artifact. Okay, so finally, the best practice. So far, I have introduced how to use ray query to implement shadows reflection to make games more realistic and immersive. To conclude, I will briefly describe a few things to help you write a more efficient ray query application. So it is important to mindful of how many rays are used and how. So as always, the advice from on is to profile early and often and measure the impact of any changes. To assist this, on offer a suite of free tools known as on Mobile Studio. Since query code appears in shader, we can use we have a Mali offline compiler to run some static analysis and find the efficient use of the API. So for instance, there are cases where the GPU cannot easily parallelize the ray traversal, and it forced to use optimize the slow traversal path. Our Mali GPU best practice developer guide, which I link at the end of this presentation, provide examples of which scenario will cause this to happen. However, if you ensure you are using a single code of a ray query, proceed for each code of a ray query initialize, and you call them unconditionally, your code is more likely to perform well. So in this example, we are calling the ray query proceed twice after a call of a ray query initialize, which means our shader will likely run slowly. The Mali offline compiler will flag this in its analysis report, as you see on the screen. All you need to all you need to do is to run the offline shader compiler executable on your shader, and you will produce a report like this, like the screen shows, with the detail of that can help you to find the bottlenecks and optimize your shader code. So in this case, for the ray query, I highlight these two. Oh, sorry. These two in red. Highlight these two relevant part of the report. We are hitting the slow ray traversal case, and therefore we will be allocated extra traversal context, which we want to avoid if you want to get the best performance. So we can simply change the shader code. In the contrast, if you have a single code to proceed after the code of initialize, we can see the report will now be updated to confirm that our traversal in the green, our traversal will likely to be fast and only use a single traversal context. So it's very important to always check your shader code using our tool, offline shader compiler. So as you can see, rather than inspect the shader manually, the offline shader compiler can help us to detect this earlier and optimize accordingly. So of course, it's not always possible to avoid this usage, but for all the effects that we have demonstrated in this presentation, we can easily avoid the slow scenario. So in our Mobile Studio, we also offer a system profiler called Streamline, which can also help you detect the friends with slow traversal and guide you to the potential bottleneck. I strongly recommend you to try these tools to optimize your application for our mobile studio. So as you can see in the screen, that's the screenshot of Streamline. So in Streamline, you can check how many rays has been casted and how many hit test has been executed and how many ray missed occurred. So those data are from the built-in counter inside the hardware. So it's very accurate. So finally, here are some best practice for getting the best performance when using ray tracing. So for both ray query and the ray tracing pipeline, first off, you should minimize the number of rays per pixel. That's the most important thing. More rays means more expensive. Okay, second, maximize the ray coherence. That means you should keep all rays in one warp and which access the same assertion structure. Then third, you can optimize the ray traversal by using GL ray flags like we did for shadow. We only want to find the first hit. We don't need to know what exactly object we hit. And for the ray tracing pipeline, first off, you should only trace the ray in the ray generation shader. Recursively tracing rays would be slow. And the second, avoid using ray query inside your ray tracing pipeline shader code. It will be very slow. And you should always keep a payload size as small as possible. And you should limit the use of any hit shader as it will slow down the ray traversal. So because of any hit shader need extra checking. So final one is consider move your implementation to ray query if possible. Ray query is more simple to implement than ray pipeline, and the performance should be better. Okay, so regarding to assertion structure, if possible, minimize the count of the dynamic meshes by reducing the number of dynamic elements in the scene. For animations, the API allows us to refit the top-level structure by updating it in place, which is faster, but it might affect the assertion structure quality. Then when we build a assertion structure, you can also provide flags that give hints to the implementation in order to use the most efficient way most efficient algorithm to build the structure. For example, use a fast trace for the static assertion structure and the faster build for the top level structure that will be updated for animations. So the API also allowed to build a structure on the CPU. So you can build the structure on GPU or on CPU. So when your application is GPU bound, you may be able to switch the building, assertion structure building to the CPU. And finally, you should double check your button level structure with less overlap. In the scene, in this simple example, notice how the way we group the geometry affect the number of boxes intersected by the ray. So in the top case, we have an overlapping structure, so they are both intersected, and we need to iterate through all the geometries. But in the bottom case, we avoid the overlap of the bounding box. So we avoid having to check almost half amount of the geometry in the scene. We only need to check the right side box, which is more efficient. So how you group your scene is very important to optimize your ray tracing code. So the last one is the link to our GPU best practice online. You can check it after the presentation. Okay, so finally, I would like to introduce some resource from ON. So first, we have an ON developer program you can join. You can ask any technical questions about ON's product in the program, and it's totally free. So you can register it now. And besides that, we also have some forums, blogs, and documentation online. So please feel free to check it after the presentation. And we also prepare some mangas to help you understand our product in fast and easy way. So the mangas have different languages, including Japanese. So please feel free to check it online. And we also provide some hard copies at our booth in CEDEC. So please feel free to visit our booth and take the hard copies. Okay, so that's all from my presentation today. Thanks for your joining today. And is there any question about today's presentation? No?
Hi, I'm Davide from Kojima Productions. And on slide 25, you suggested...
25?
Yes. You suggested to move to ray query instead of ray tracing pipeline. I'm mostly expert with desktop, but I've read a lot of best practice, also ARM best practice, the Vulkan documentation. They say the opposite. It's like, please move to ray tracing pipeline. So my question is this for simplicity only? Because I agree, ray query are much simpler. Or is like on mobile, your company is optimizing more for ray query instead of the pipeline?
I think both, but most important is simpler. And you don't need to change your whole pipeline. Because ray tracing pipeline, you need to write the new shader code for any hit.
Yes, I use a lot of callable shader to do that.
And it's a separate pipeline from your graphic pipeline. So it's more difficult to implement, and you need to change a lot. If you already have a engine, you need to change a lot. So ray query is much easier. You can just add it into your fragment shader, current fragment shader. So I think that's why. And when you are trying to use a hybrid rendering, you want to use rasterization to render the best image, then add the effects of ray tracing on the rasterized image. So it's a easy way to do it.
Okay. I have another question, same slide, about maximize ray coherency. And you kind of gloss over this topic, but can you elaborate more? Because I think there is, I would like to know some metrics about the performance of packing rays together. Like, is there any big performance difference if I somehow manage to hit all the same region instead of, for example, having a reflection that goes around the scene in different parts and need to access different resources?
Yeah, in this case, it will be slow. So, but if you only have one assertion structure to present your whole thing, that should be okay. But if you have more than one, then if the shader need to traverse two or more structure as assertion structure at the same time, it could be slow. Yeah, especially for mobile. Yeah.
And for mobile, now you are just investing in small scene with small acceleration structure, because the memory is enough to fit the entire scene.
Yeah, I think that's because if you traverse more assertion structure, we need to allocate more memory for the assertion structure. Yeah, so that could be, and we need to switch. So because in one WAP we all run the same shared code. Yeah, so if there are some different contexts, yeah, it will be slow. Yeah.
Okay, thank you very much.
Oh. Read out the question. So the question is about is there any way, because it's quite difficult to avoid the GPU divergence because each pixel forward a different path. So is any way to avoid it? You say NVIDIA has launched a shared execution recoding for this problem. Yeah, so far we don't have the solution yet for that yet. Yeah. So probably we will try to resolve it later, but we don't have any tools or any suggestion for that yet. Yeah, I know it's really hard to avoid diversity when you're doing the ray tracing with the reflection. Yeah. So we don't have the resolution yet, but we will check this later. So I have sorry. I have a email here, so you can send me an email about this, and I can check with our internal team to see if we have any plan for this. Yeah. Yeah, but for now, our suggestion is try to avoid the GPU divergence for best performance. Yeah.
This is the reason why in the demo there was only refraction, not refraction and reflection.
Yeah, but that in our demo we only have one assertion structure, so this should be, yeah. Yeah, I will forward this suggestion to our internal team to see if we can have some tools in the future. Okay. So I think that's for today. And after this session, we will still have online session for answering your questions. So if you have any question, you can input it online. So I will answer it later. Okay, thank you for your joining today. Thanks.
応援ウー様、ありがとうございました。以上でセッション終了となります。